So in the past, we learned that average speed of an object is the distance traveled divided by the time elapsed. Now for motion along the circular path, we distinguish between linear speed and angular speed. Consider a circle with radius r and an object traveling around it at a constant speed. The distance traveled around the circle is denoted by S, and the speed is denoted by V. This follows that S equals V times T. So if you have a circle and you have a part of a circle, which is the arc, so that is the size, the linear distance of that arc. A good example would be, let's say that if you cut a piece of dental floss, okay, and you make a circle out of it. So part of that dental floss, if you just look at the portion of it and look at it, open it again, then that is the arc. That's the linear distance. So S equals V times, or velocity times time. That follows that T equals that arc, or the linear distance of that arc divided by velocity, and velocity is S divided by T. Let's go to page 4. Now, as the object travels around the circle, we can measure how fast the angle theta is swept out. How fast is that theta growing? Okay, so let me go to the next page, go to page 5. I hope you can read my handwriting. This angular speed is denoted by omega, which is kind of curvy. W is Greek, and is equal to the theta divided by T. So omega equals theta divided by T, T equals theta divided by omega, and theta equals omega times T. You got to remember that here theta is in radians, not degrees. You must be in radian mode. Let's go to page 6. So noticing that both linear velocity, that is S divided by T, and angular velocity omega, that is theta divided by T, they have T in common. So and considering the fact that S, or the size of the arc, equals radius times theta, now we can do some algebraic manipulation. Notice that here, this V equals r theta times T. That's given to us. We already talked about it. So if I factor an r out, now that equal, if I factor an r out, then I have r times theta over T. And what is theta over T? Theta over T is omega. So that results, so V equals R omega is a nice formula for us to use. In summary, the following, let me go to page 7. The following formulas are really nice to use. I put everything here for you. And now I'm going to go ahead and go to the next page and do an example. So let's go to page 8. An object is traveling around. An object is traveling around a circle with a radius of 2 meters. If in 20 seconds the object travels 5 meters. What is the linear speed? What is the angular speed? Doesn't matter the order. So let's do what is the angular? Let's do that one first. What is the angular speed? That would be omega. And what is the linear speed? What is the linear speed? Okay. So let's go to page 9. So we do have a circle. The radius is 2 meters. That's our, given to us. So we know that R equals 2 meters. T is given as 20 seconds. And S is given to us in 5 meters. Okay. So what is the angular speed? Omega. Omega equals theta divided by T. So you can say that omega equals, what is the theta? Theta is S divided by R and divided by T. So S is 5, radius in this case is given to as 2 divided by 20. And that simplifies, let's see, if I multiply top and bottom by 1/20, 1/8, and that's going to be radian per second, radian per second. So the angular speed, omega, that's how fast the theta is growing, is 1/8 of radian by second. Let's go to the next page. And linear velocity. V equals, we said V equals S divided by T. And that equals, S is given as 5, T is going at 20. So that's 1/4 meter per second. So the linear velocity is 1/4 meter per second, and the angular velocity was 1/8 of a radian per second. I'm going to go ahead and show you the pages in case if you would like to see them again. So this was page 1 of the notes that I made from different textbooks. So let's go to page 2. Let's go to page 3. Page 4. Page 5. Page 6. Page 7. Page 8. Page 9. And the last page, page 10. And this actually is 1/4. Okay, I'll talk to you soon. Thanks.